Hello everyone, this is Dr. Lennon, and this is the last topic we're going to be looking at for the course, so kind of the end of our applied calculus. We looked at antiderivatives last time, so let's recall. Last time, let's say given a function f of x, we say capital F of x is an antiderivative of little f of x, provided if you take the derivative of this capital F of x, we get little f of x. So that's just a quick recap. We looked at the example. We looked at the example. So if f of x was x squared, then f of x equals x cubed over 3, or 1/3 times x cubed, plus c, where c is any constant, is the general antiderivative of f of x. So that was the example we saw. We're going to see polynomials behave pretty regularly like they did for the derivative formula. So if we think about the derivative formula for polynomials, so the derivative formula for x to the n, which we call the power rule, what did this do? It says, well, if you take the derivative of x to the n, then what that means is, what we do is we bring the exponent down, n, and then multiply it by the same variable x, and then now this is raised to the n minus 1. We lower the exponent by 1. So first we brought down the variable, or the exponent in front, and then we subtracted 1 from it when we had a monomial like that. So the antiderivative formula is basically going to do the same thing, but in the completely reverse order. So it's going to reverse all the processes. So instead of multiplying, now we're going to be dividing, and then instead of subtracting 1, we're going to add 1. And what did we do first? We began by multiplying, so multiplying that n in front. So in effect, what we do now is we add 1 to the exponent before we start the division. So the antiderivative formula for x to the n is going to be, and let me reuse that integral notation we did for areas. So we'll see this with the fundamental theorem more concretely when it comes to definite integrals, but we use that integral symbol. That means find the general antiderivative, and then we put a dx next to it, representing the differential, which is, again, applying the limit to the width of all those rectangles when we're thinking about doing the Riemann sums. But what is this formula? Well, we take the x, we add 1 to the exponent, and then we divide the entire quantity by that new exponent. We have n plus 1, and then we add c to it, and that is the general antiderivative. So if you look up at the example there, if you did the integral of x squared, we added 1 to the power, and then we divided by 3. So that's why we got the x cubed over 3. So let's just make a quick comment on that notation. So notation. The indefinite integral of a function let's say f of x is denoted by, if x is our input variable, it's the integral symbol of f of x and then dx. So this asks us to compute the general antiderivative of f of x, of little f of x. Okay, so let's look at just some examples with these polynomials, or technically they're not even polynomials. We can do it with any power function, so basically x to any power, except for one special case. But let's look at some examples. So we'll just say compute each indefinite integral. So A, let's say we have, let's suppose we had f of x was equal, well, I said indefinite integral, so let's write it using the notation. So let's say we did the integral, and instead of writing f of x and telling you what it is, we'll just write the formula in between the integral and the differential. So what is the antiderivative of x, the general antiderivative? Well, the power of x here, since it's not written, is actually just a 1. So if you add 1 to 1, you get an exponent of 2, then we need to divide by that number. So we get x squared over 2 plus a constant. What about if we had something like the integral of 3x to the 4th dx? Well, I haven't mentioned this yet, but basically the integral is going to work well with all the same things that the derivative worked nicely with. So sums, differences, and multiplication by a constant. So basically the integral is going to be a linear operator with respect to its inputs. So what we do here is we just take that 3x to the 4th and just focus on x to the 4th. So we're going to add 1 to that exponent. So we get 3x to the 5th, and now we divide by that new exponent of 5. So that would be our antiderivative. And then C, let's suppose we had the antiderivative of 1 over x squared. Now this doesn't look like our other examples, but we can in fact write 1 over x squared as x to a power, right? 1 over x squared is the same as x to the negative 2. So if we rewrote 1 over x squared as x to the negative 2, then we could use the same trick. So what we'd want to do is add 1 to the power. So negative 2 plus 1 is negative 1. So we get x to the negative 1, and then we divide by negative 1. And then add our constant. And remember, multiplication or division by negative 1 is the same thing, and x to the negative 1 is just 1 over x, so we could actually write this as minus 1 over x plus c, and that would be our final answer there. So let's think about, let's make that comment first. So comment, okay, so let's suppose, let's say f of x and g of x are continuous functions. Basically, the nice thing about continuous functions is you can always find an antiderivative form. They're always integrable. And let's say k is a constant. So what are the properties we have here? So the following 3 properties are true, let's say. And again, they're analogous to ones we have for the derivative. So if we have the integral of 2 things that are added together, say f of x plus g of x, we can split this up into each part separately. So we can look at the integral of f of x dx, and then we could also look at the integral of g of x dx. We could do the same thing with subtraction. And do each one piecemeal. So the integral of f of x dx minus the integral of g of x dx. And then we could also look at multiplication by a constant. So if we have the integral of So some number k times f of x dx, this would be the same as if we pulled the k out and did k times the integral of f of x dx. And technically we were implicitly using that when we did property number example b above. So the 3 was in front of the x to the 4th, but we really just focused on the antiderivative of x to the 4th, which is x to the 5th over 5, and then multiplied the 3 back at the end. Okay, so basically now we can take the antiderivative of any polynomial. So let's just do one example. So let's just say compute the integral of, let's say, 12x squared minus 8x dx. So that's all we have to do here is the same trick, add 1 to the exponent and then divide, and then we do it separately. So I'll write this down as 2 steps so we can actually make this into 2 separate antiderivatives. In general, most people are not going to write this part down, but just to see that we're applying property number 2 above, and then if we want to apply property number 1, we can bring the 12 out front and write this as the integral of x squared dx, and then bring the 8 out front for the second integral, and then write that as the integral of x dx, and then do both of those antiderivatives. So we would get 12 times x cubed over 3 minus 8 times x squared over 2 plus our general constant, and that would leave us with 4x squared minus 4x cubed minus 4x squared plus a constant. And that would be it. So probably most people could do that in 2 steps, just moving directly to the last 2 lines. But if you write the first 2 lines, you can see exactly how the properties are being used. So this is by property number 2, and this one is by property number 3 applied to each integral. So let me add 2 little things that we haven't talked about in terms of polynomials if we wanted to integrate any polynomial. So here's a question. Remember, the antiderivative is just kind of the derivative in reverse. So what kind of function has a derivative equal to 0? So we saw that so any constant has derivative 0. So that's one reason that we're always sticking a constant on the end to represent the family for the entire family of general antiderivatives. And those are the only functions that have derivative exactly equal to 0 over their entire domain, over all real numbers. So then the other question is, what function has derivative equal to a constant? And the answer here is basically any linear function so you could think about that if you took the derivative of, say, something like mx plus b. Here both m and b are constants. B is by itself, so it would have derivative 0. M is multiplied by x, so the rate of change is just the slope in front there of m. So the takeaway from this, kind of the corollary, is that means if we take the antiderivative of any constant, the antiderivative of some constant function, we would actually just get, well, maybe c is a poor choice because we use c for the general constant that you add in for the family of antiderivatives. So let's say k. Then the antiderivative would be kx plus c. So let's just build this into a polynomial example. So let's say we want to compute the antiderivative of 9x squared plus 5x minus 3. And then basically we just do each part separately, right? So this time I'm not actually going to write them all out and specify the properties. The first part would just be 9x cubed over 3. The second one would be 5x squared over 2. And 3 is a constant at the end, so that would be minus 3x and then plus a constant. So that would be your basic antiderivative. Okay, so let's think about the other functions that we've had previously. So let's look at exponential functions. So the exponential derivative rules. And then we'll kind of reverse the process and get the exponential antiderivative rules. So for the exponential derivatives, we have a few rules. We said if you took the derivative of e to the kx, the continuous form, this would be k times e to the kx. So what did we do here? That's all we did is we took the constant and the exponent and we brought it in front and multiplied it. So the analog to that would be if you had a, if we were trying to find the antiderivative of e to the kx, rather than multiplying, we would just divide by that k. So this would have antiderivative e to the kx over k plus a constant. And the other one, if we had something in standard form, say b to the x, this had derivative natural log of b times b to the x. So again, since we multiply by the natural log of b, which is in fact just a number, for the antiderivative for this class of functions, we would just be now dividing by the natural log of b. So this would be the b to the x divided by the natural log of b plus our arbitrary constant. And that would be that. So we could look at a couple of examples of finding these antiderivatives. So let's just say compute. So let's say A, we have something like e to the let's say 3.5x dx. Well, our antiderivative now would just be e to the 3.5x over 3.5 plus a constant. And that would be that. And say we were trying to find the antiderivative of, I don't know, 8 to the x dx. We would then have 8 to the x, and then we're dividing by the natural log of 8 plus a constant. So the only difference here is A is in continuous form, so we use the rule number 1 above, and B is written in the standard form, so we're going to use the second rule. Okay, so one last rule maybe we'll look at. So what is the other function we looked at? Well, we said the derivative of the natural log of x, we had a rule for that. So if we took the derivative of the natural log of x, this actually came out to 1 over x. So that means if we were looking at 1 over x, we could find the antiderivative of that. So this corresponds we can go the reverse order. So if we're trying to find the antiderivative of 1 over x dx, this comes out to the natural log of the absolute value of x plus a constant. And again, remember the domain of the natural log are input values greater than 0. So if you happen to have some function where you know that the input is going to be greater than 0, you don't have to have the absolute value, but otherwise you need to make sure that the domain agrees with what you're finding the antiderivative of. So we have that absolute value there for that reason. Anyhow, if you try to use, say, the power rule, you said, well, 1 over x I can write as x to the negative 1. You can't use that power rule because if you took negative 1, added 1 to it, you would get x to the 0. Then you'd have to divide by 0, and that doesn't really make sense. So using the understanding that the antiderivative is the derivative in reverse, since we know the natural log has derivative of 1 over x, the antiderivative of 1 over x will be this natural log of the absolute value of x. So those are the derivative rules for the basic classes of functions that we've looked at in applied calculus thus far. So we want to get to the last point, talking about the fundamental theorem of calculus here. So how does the antiderivative tie into these areas below curves? So here is the part of the fundamental theorem of calculus we're doing. So technically this is part 2 of the fundamental theorem of calculus, but it's the only one we're going to be looking at. So if f of x is a function that is continuous on AB, and capital F of x is any antiderivative of f, then the definite integral from a to b of f of x dx is found by doing f of b minus f of a. And also recall that the integral of a to b of f of x dx gives the signed area between f of x and the x-axis. So let's see how this works in a very concrete example. So the example we want to look at, we could say find the area below y equals x squared from x equals 1 to x equals 3. So what's going on here is we know the curve y equals x squared is just the parabola with vertex at the origin. So, we've got some picture like this. It's not the best picture, but you get the idea. So let's say this is 1, 2, and 3. Then basically if you would look at the curve between 1 and 3, we're trying to find this area right here. So that area is given by the integral from 1 to 3 of our function here, x squared dx. We know how to find the antiderivative. That's x cubed over 3. Again, we can use any antiderivative per the fundamental theorem of calculus. So when we're doing these definite integrals, meaning we have limit points at the top and bottom of the integral, we can always just kind of disregard the c. Since we can choose c, it's always easiest if we choose c equals 0. So then what you do is we plug each one in for x and then subtract them. So we get 3 replaces x to the third power over 3, and then subtract, and then 1 replaces x to the third power over 3. So this ends up being 9 minus 1/3, which comes out to 26 over 3, or about 8.67, something like that. So that's it. That would be the exact value of the area. If we tried to use a rectangle approximation, we probably would get something maybe like close, but not exactly correct. Using this method, we can find the exact area so long as we know how to find the antiderivative. So let's do a couple more examples, and that'll be it. So example, let's maybe find the area below, let's say y equals e to the 0.2x from x equals 3 to x equals 4. Again, I'm not going to draw the picture this time, but maybe I will. The picture's not so hard. We just kind of have a flattened version of our typical exponential curve. So we've got something like this. We've got 3 over here somewhere, and we've got 4 over here somewhere, and we're again just trying to find an area. Exponential functions, we know, are always going to have a positive y value, so the area here is going to just be the antiderivative from 3 to 4 of this formula e to the 0.2x. So we find our antiderivative using that new rule. So we have e to the 0.2x over 0.2, and then we have our limits. So then what we want to do is plug in each of those limits for x and then subtract. So we get e to the 0.2 times 4 over 0.2 minus e to the 0.2 times 3 over 0.2. And at this point, we're just going to appeal to our calculator and approximate to, say, 2 decimal places, something like that. So we get e to the 0.8 minus e to the 0.6, with everybody being divided by 0.2. So we get about 2.017. Let's use 3 decimal places. And that would be our answer. And you can even use these things to find areas between curves, and that relates to some of the linear principles that we talked about before for the integral. So let's do one last example. So let's say find the area between, let's say, y equals 3x plus 4 and y equals x squared from x equals 0 to x equals 1. So what's going on here, again, a picture is going to be helpful. On the one hand, we've got our parabola y equals x squared. We know that looks something like this. So going from 0 to 1. And then we have 3x plus 4. So that has a y-intercept somewhere up here of 4. And then it's going up 1 over 3. So, we've got this line going here. So we've got a linear function and a parabola. And essentially what we're trying to do is we're trying to find the area between the two. So we're trying to find this shaded area right here. And since we know that the 3x plus 4 is on top, what we can do is we can just subtract the two functions. So the area here is going to be the integral from 0 to 1 of this 3x plus 4 minus x squared dx. And then you just find the integral as usual. And again, the line is on top. That's why we are putting it on top and then subtracting the formula for the parabola that's on bottom. So this would be the integral from 0 to 1 And we could write it without the parentheses because there's nothing to distribute. So minus x squared plus 3x plus 4. So we find our antiderivative, which is going to be minus x cubed over 3 plus 3x squared over 2 plus 4x. And we're going from 0 to 1. So if you plug in 1, we get minus 1 cubed over 3 plus 3 times 1 squared over 2 plus 4 times 1. And then when you plug 0 in, plugging 0 in for x, when you have a polynomial like that, just creates 0. So we're really just subtracting 0. So that second part makes the computation relatively simple. So we end up with, let's see, 5.5 minus a third, which if we want to approximate with a decimal, we could say that's about 5.17. So let's use the approximate value there. Well, I suppose we could also turn it into a fraction if we want. So we could write it as either 31 over 6 or approximately 5.17, whichever you prefer. Anyway, that's it. So that's the big connection between the antiderivative and the problem of finding the areas under curves. So that's solved by the fundamental theorem of calculus. So this is Dr. Lennon signing off.